This lecture is called The Lives of the Stars, or more accurately, the lifetimes of the stars. What controls the lifetime of a star? In the case of the sun, we just worked it out. We figured out the total amount of fuel available. We know the rate at which the fuel is being converted by nuclear fusion reactions. And so we figured out that it was a long time, 10 billion years. And we're a little bit less than halfway through that. What about other stars? I said the sun is typical. It turns out, though, that stars vary widely in how long their main sequence lifetimes will work before they've burned out all of the hydrogen in their cores and converted into helium and are out of fuel in their cores. And it all comes down to how fast they're burning through how much of a fuel supply. And I've told you several times now, but I'm going to explain why. It's the mass of the star that determines this whole process. The mass tells you everything about how a star is going to evolve and how long it's going to be before it dies, or I should say, before it runs out of fuel and exhausts it in the center. It's all burned into helium in the core. Why is that? Let's think a little bit about those nuclear fusion reactions we talked about before. Remember that Eddington realized in the case of the sun that it was a very close thing, very marginal, whether two atomic nuclei, let's be specific, two protons, whether two hydrogen nuclei or protons could just barely get close enough together to overcome their natural electric repulsion so that they can have a fusion reaction take place. And it's a very crucial function of how fast they're moving, how much energy of motion they have. The random energy of motions inside the center of the star, that's the temperature. So if you could somehow increase the temperature a little bit above, say, the 15 million degrees it is currently in the center of the sun, that means the collisions would be more violent, there'd be more energy hurling these protons together, and they would more often get closer together and they would more often fuse. And this is a very sensitive effect because they're just right at the boundary now of barely having enough speed to get close enough to each other, thanks to the uncertainty principle, to grab each other occasionally. So, for example, let's take a specific example. If a star like the sun were for some reason twice as hot in the center of the sun, it would generate, well, a lot more nuclear fusion reactions. It might be something like 20 times more power generated by the same nuclear reactions because they would go so much more frequently than they do in the sun. Well, how could that be? Why would a star have a much higher center temperature than the sun? Oh, that all gets back to the gravitational equilibrium, the balance between the gravitational force that's trying to crush the star into its center versus the gas pressure that's just in balance to hold it out. The more gravity you push in, the more the gas pressure will have to push out to establish an equilibrium between those two forces. Now, you see where we're going with this? That means the more massive the star is, the more gravity pushes in, the hotter it gets in the center. It's a little bit like the principle of a diesel engine. You compress something down, it gets hotter in the center. More compression, more gravity, more hotter in the center. And so it does come back to the mass of the star. A sun that has considerably more mass than the sun, a star that has more mass, will be hotter in the center and it will generate much more luminosity. It's a strong function of the mass. The total power generated by nuclear fusion reactions for a main sequence star goes, you don't need to know this, it's something like the fourth power of the mass. So, for example, a star that's just twice the mass of the sun, not that unusual, would be, as I said before, 16 to 20 times more powerful than the sun. And, of course, the opposite is true also. If you decrease the mass of the star below the sun's mass, the nuclear fusion reaction rates go way down, and the luminosity, the power that's produced in watts, goes way down also. So a star that's half the mass of the sun is only putting out about 1/20th as much power as the sun is. So it really makes a big difference how much the mass is. It determines exactly where that star will be for most of its life on the main sequence. Remember the main sequence? The main sequence is this graph that has on the vertical axis, the y-axis shows how much power the sun is putting out. In this graph, we have it normalized to units of the sun's power, 4 times 10 to the 26 watts. There is the sun there. And as you can see, there are stars with 10, 100, 1,000 times more power than the sun. What does that mean? They must have more gravity, higher central temperatures. These are the more massive stars. So the sun will sit here pretty much on the same part of the main sequence for most of its lifetime, billions of years, not doing much, giving us a nice, steady, dependable, reliable source of power. A more massive star will sit here belting out much more power, but not moving on the main sequence until it runs through its fuel supply. The main sequence, we now realize, when you look at the stars carefully, is a mass sequence. And stars up and up and up the main sequence are more and more and more massive than the sun, and that's why they're there. Stars below the sun, down here on the redder part of the main sequence, are smaller mass than the sun. And so they have less nuclear power generated in their cores. That's what the main sequence means. So here's the money question now. Since we see that the amount of fuel, of course, goes up and down in proportion to the star's mass, that's how much fuel is available to burn. But the burn rate, the consumption rate of the fuel, which is the power of the star, varies much more widely. And remember, the temperature, the lifetime of the star is the ratio of those two. Fuel supply divided by consumption rate. So what does this imply about the lifetimes of stars having different masses from the sun? There's a clear prediction if we understand nuclear fusion reactions in stars, and we understand gravitational equilibrium, which is pretty basic physics there. We ought to be able to understand that. What are we predicting then about the lifetimes of stars more massive than the sun? It's a very clear prediction, and it's a little bit ironic. I mentioned this before. Even though those stars have more mass, so they have a bigger fuel supply, they're ripping through the fuel supply so much faster that they will run out earlier. They will run out much earlier and have a considerably shorter lifetime than the sun. So as you go up this mass sequence, again, it's ironic. They start out with so much fuel, but they burn through it so fast, like a rich prodigal, heiress or something, blowing through all of her fortune, or his fortune. It can go either way. It's all gone much shorter than 10 billion years. So as you go up the main sequence, the lifetimes drop down to 1 billion years, at about there, and then hundreds of millions of years. And for the most massive stars, these might be 10 or 20 times the mass of the sun. The entire lifetime on the main sequence might only be a matter of millions of years. Okay, I know you think that's long compared to human history, but compared to the sun, it's just an instant, a flash of cosmic time. How about stars that are less massive than the sun? I know what you're thinking intuitively. They've got less mass, less fuel. Wouldn't they burn through their fuel supply quicker and run out quicker? It's exactly the opposite. These low-mass stars are so miserly. They don't have much, but they are very stingy with expending that hydrogen and burning it into helium at a very slow rate. They will actually live much longer than the sun. The lifetimes of these stars can be hundreds of billions of years, much longer than the age of the universe. Some of these stars seem like they're practically immortal. They're not doing much, but it will be a long time before they ever run out of hydrogen fuel in the core and end up finishing their main sequence lifetimes. So this mass sequence then, that's what controls things, the main sequence, is a lifetime sequence. Now I wonder if there's any way we can test these ideas. I gave you a lot of ideas. They're based on our understanding of physics and fusion. But nobody has actually ever done a thesis project to measure one of these stars going through its main sequence lifetime. That doesn't sound like a very good PhD project, does it? I'm going to wait for this massive star to evolve and die, or see what happens when it leaves the main sequence, when it's exhausted its hydrogen supply. Darn, I mean, talk about a long graduate student career. You'd have to be waiting millions of years to actually see that happening. And even the most patient graduate students I know, and the most patient departments, are not going to allow that long a course of study. Let's suppose, for example, that you were a botanist and you had the job of understanding the evolution of trees. Now, trees, of course, take years to grow up and then years to live in a mature state, years to die, and so on. And that has been studied, by very careful botanists, I guess, that go around and measure trees at different ages and come back after years and so on. They can actually figure out the life cycle, the growth history, and maturity of a tree. Now, astronomers are in a very awkward position here. Suppose that you were a botanist who wanted to understand the whole evolution of trees. And I let you go into a forest that had thousands of trees, and I said, you can make any measurements you want of these trees. You can measure their size, their mass, how they're doing, and you can try to gather as much information as you can on your visit to the forest. I'm going to let you visit it one time, and then you're going to have to come back and work out all the details about how trees evolve. Oh, and guess what? Your entire visit, the entire length of your observations of these trees is going to last for 1 second. That's it. That's all you get to understand how trees grow and evolve and die. Tough problem, wouldn't it be? That's exactly the problem that astronomers have when we're looking at phenomena that take millions and even billions of years, and we only get to observe them for a few decades, maybe. What's the solution? We have a special natural experiment that's being done for us, which gives us, in effect, an equivalent of what a botanist would like to have, a whole forest of trees that were all planted at the same time. That would be very interesting. That would be very useful. And that is, in fact, what astronomers have the direct analogy is a star cluster. This is how we can test how the mass of a star controls its lifetime and determines how long before it dies, before it runs off of the main sequence, exhausting its fuel supply. All right, so this is the theory that I gave you. This is the third test now. We've done a test on neutrinos. We've done other tests generally confirming the idea of nuclear fusion. This was the most critical test. This test that was really done in the 1950s and 1960s when people began to understand fusion reactions fairly accurately and actually measure some of them in laboratory situations. This was worked out by a detailed study of stars in star clusters. Now, what's the advantage of having a star in a star cluster? I'm going to skip that. A star cluster is a natural experiment where you have hundreds or thousands or maybe even hundreds of thousands of stars. They have a number of advantages. First of all, they're all at the same distance from Earth. So that's very convenient. Sometimes we don't know the three-dimensional distance of things, but at least when you're looking at a star cluster, since they're all the same distance away, the relative brightnesses of the stars is exactly equal to their relative power, or their relative luminosity. If you see one star that's 10 times brighter than the other, since they're at the same distance, that brighter star is 10 times more powerful than the fainter star. So that's a nice simplification. They're all made of the same chemical elements. That's a small but useful detail. And here's the most important thing. It turns out that these star clusters were all born together. They're all like siblings of a giant batch or brood of stars that formed at about the same time. And so they've all been evolving for about the same amount of time, so they're all the same age. In fact, what's the only difference between the various stars in a star cluster? What's the most important difference? They differ in the mass with which they were born. Star clusters form lots of low-mass stars, some average intermediate stars with mass like the Sun, and then relatively small number of very massive stars, and they're all formed together. That's what's so useful. So we have a collection of stars with the same age, but since they have different masses, we predict that they should have different lifetimes on the main sequence. And we can test this. How will we test this? We need to measure the fundamental basic properties of the star. We need to measure, of course, their luminosity. That's the rate at which they're producing nuclear power. And we need to measure, it would be useful to look at their surface temperature as well. In other words, we'd like to look at a Hertzsprung-Russell diagram or a luminosity temperature diagram for all the stars in a star cluster. All right, so as I explained, we know their relative brightnesses are telling us their relative power, and they're all coeval, as that's the technical term. All right, here would be one example of a star cluster. This is a nearby one. You can see some of these bright stars with your naked eye. That's the Pleiades there, and it's called an open star cluster. It has hundreds of stars. Now, this particular cluster, I can tell you, is about 80 million years old. I wonder how astronomers were able to figure that out. That's interesting. Now, if we just had one star cluster, that'd be like just one forest that we could study, but fortunately we have many of them. And here's the beauty of it. We have many star clusters that were formed throughout the history of our galaxy, throughout the history of the universe at different times, having currently today different, very different ages. That's what I want. So there's a relatively, compared to cosmic time, compared to the age of the galaxy, that would be a relatively young star cluster. There's one of the oldest ones. I love these star clusters. Did some research work on these in college, and I'm still pretty fascinated by them. They're beautiful to look at through a telescope. 1 million stars in this star cluster, all bound together by their mutual gravitation. So they're all orbiting in rather elliptical orbits around the center of mass here at the center of the cluster. And the remarkable thing is that they were all apparently formed out of one very large ball of gas a long time ago, and the globular clusters, they're called globular star clusters. I guess they look kind of globular. The typical ages of globular star clusters in our Milky Way galaxy are, I'm going to say, something like 10 or 11 billion years old. So the globular star clusters that orbit around the Milky Way are the oldest objects in the known universe. All right. So I've shown you now young star clusters. I've shown you old globular star clusters. What do you think their Hertzsprung-Russell or luminosity surface temperature diagrams would look like? They have a main sequence, but it looks quite different between these two collections of stars. I'll show you some actual data here. This is sort of a little schematic of actual data of the HR diagram of the Pleiades cluster here. Each one of those dots is a star represented in this diagram, where, of course, the vertical axis is how much power the star is putting out in units of the sun's power there. So we have some stars that are very much like the sun, and we have lots of stars that are more powerful, even 100 or 1,000 times more powerful than the sun, which are on the main sequence. Then we have some less massive stars down here going down to 1/10 or even 100th of the mass of the sun, and so they have low surface temperatures. Interesting lines that are put on this diagram. These lines are a deduction of what the size of the star is, just using Stefan's formula. Remember, from my previous lecture, Stefan's formula is the amount of power produced by a black body. These stars are approximately black bodies of these different surface temperatures. So if you have a given surface temperature here and you take that to the 4th power, that tells you how much luminosity or power, watts, is coming out per square meter. Now, as the stars get hotter and hotter here, each square meter is putting out much more power. So the stars, these upper main sequence stars, aren't that much larger than the sun, but they're much more luminous. They're hundreds or thousands of times more luminous than the sun, simply because each square meter is hotter, putting out hundreds of times more power than a square meter on the sun does. So this main sequence is, to some extent, a sequence of stars of similar size. There's the size of the sun, solar radius, and some of these stars are a few times bigger, these are a few times smaller. But anyway, I just wanted to clue you in on that, because we are going to encounter some stars later on after they leave the main sequence, after they exhaust their fuel supply, which will be way off the main sequence, totally different sizes. But we haven't gotten there yet. No, we're almost getting there. Okay, and here is a old globular star cluster. And sorry, we don't have. I got to get some better observations to show you. There is a main sequence down here of stars, just like there is in the Pleiades. There's lots of low-mass stars, which are now on the main sequence, and that shouldn't be too surprising. I told you those stars will live on the main sequence practically forever. Hundreds of billions or a trillion years. So, of course, they've just been sitting on the main sequence all this time, and they're going to sit there a lot more time than we can wait around to watch them. But the one thing that you'll immediately notice that's different about the globular cluster is there's no upper main sequence stars. What happened to all these blue stars? These massive stars no longer found in, I should say, they are in the star cluster, but they're no longer producing light that we can see. They're no longer shining on the main sequence. In fact, here's about the last stars here. This diagram isn't really showing you this very precisely. The last stars in a typical globular star cluster, which are still on the main sequence, that's the termination of the main sequence, is approximately at the temperature and the luminosity and the power of the sun. What does that mean? Can you see this? The Pleiades is a young star cluster, so even stars that have fairly short lifetimes on the main sequence are still in their main sequence phase, except for a few of the most massive stars that have lifetimes of less than 80 million years. They're finished. They're off the main sequence. These stars are leaving the main sequence. The last stars that are on the main sequence, just the last ones, they're just about to croak. They're about to go off. They must be just at the end of their main sequence lifetime. You tell me where the main sequence of a star cluster ends, terminates, turns off. I'll tell you how old it is. It's the age of those stars in the main sequence. And now you can immediately see I've got a star cluster here, a globular cluster, where stars of the mass of the sun are now ending their lives. They're finished with their hydrogen fuel supplies in their core. But we claim we know very accurately how long that takes. How long did we say that the sun will last burning hydrogen to helium in its core? Remember? 10 billion years. And those stars have been through it all in the globular star clusters and are now wrapping it up and packing their bags and heading out. So how old are these oldest star clusters that are known? How old are the typical globular clusters in our galaxy? They must be 10 billion years old, meaning obviously that the universe must be at least that old, because you can't have stuff in the universe which is older than the universe itself is. You can't be older than your mom, so to speak, although some moms might like to pretend that for reasons of personal vanity. All right, so now I hope you see how powerful a test looking at the main sequence, particularly the main sequence turnoff of different age star clusters is. So here's what's actually happening now. I told you that the main sequence is a mass sequence. Now I'm going to put down some numbers here. Let's see. There we're starting with the sun's mass, and then you see that's pretty much what I said. As you go up to just twice the mass of the sun, you're already 10 or 15, 20 times more powerful than the sun and hotter on the surface. And so these stars up here are only going to last about 1 billion years. They have about 1/10 the lifetime of the sun. Then we go up further here, stars that are putting out energy on the main sequence 1,000 times faster than the sun. They don't have that much more fuel. So these stars have 100 times shorter lifetime than the sun, 100 million years. Finally, you go up to these stars that are belting it out at 10,000 or 100,000 times the luminosity of the sun. These guys are going to be all done with their fuel supply in a matter of millions of years. I don't hardly know any stars that are definitely 120 times the mass of the sun now. They live such a short time. They're so rare. There probably have been some. There's a few of them around in the galaxy. And this diagram doesn't show you, but there are lots and lots and lots of cooler stars down here that have masses less than the sun. So now let's look at an interesting little animation. You have to watch this animation pretty closely and pretty carefully to see what's going on. Here is an actual model, pretty realistic model using our best estimates of stellar evolution of a star cluster. This looks like we've got, I don't know, 10,000 or 100,000 individual stars here. Each dot here is a star. So I've got a whole range of stars. Now we're looking at the star cluster just at the moment that all of those stars were born. So the age of this star cluster is approximately 0 years old here, because even the most massive stars are still going through their very quick, short phase of life on the main sequence here. So this is the very beginning. Now I'm going to play a movie here which lets time pass. And time will pass in this movie at an astronomical rate. I guess it's a few million years per second. What do you expect is going to happen? In other words, we're going to, in front of our very eyes here, we're going to let this cluster age. And we're going to see what happens to different stars. These low-mass stars down here, I don't think anything's going to happen to them for a long time. They have very long lives on the main sequence. They'll just sit there happy to generate power. They don't have a lot of fuel, but it'll last them a really long time. Which are the first stars to go? Which are the first stars that are going to peel off the main sequence, exhausting their supply? These very short-lived stars up here at the high luminosity, high temperature end of the main sequence. And since this movie is going millions of years per second, you're going to notice a flash of activity. These stars literally will just die in like a cosmic flash of time. That's why I wanted to show you the movie before it gets started. These stars are just going to die like flies. Bam, 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 bam. Systematically, the most massive ones first peel off, then the less massive ones, and the less massive ones, because the further you go down the sequence, you're getting to lower masses, which ironically means longer lifetimes. So then, finally, this furious process will start to slow down, because the movie is only going, like I said, millions of years per second. So finally, by the time we get to here, and the lifetimes are, tens of millions of years, hundreds of millions of years, the death rate won't be so radical. It won't be so dramatic here, and things will seem to slow down. And the movie, this is literally true, the movie will appear to slow down. Then you have to start waiting hundreds of millions of years. And finally, when you get down to here, you have to wait billions of years. I'm going to let the movie play. Let's see, it looks like it runs for almost a minute. So we're going to let the movie play for a number of billions of years, and you'll gradually see more and more of the main sequence dying and peeling off. And at every moment that you were to look, suppose these are different star clusters of different ages, at every moment you look, the last main sequence stars that are just ending their life and turning off the main sequence tells you the age, the current age of the star cluster at the moment that we're looking at it. All right, ready for all of this action to happen here? Okay, I'm going to let it loose. And like I said, you're going to see before your very eyes, you're going to see the main sequence stars peel off from top and gradually eat their way down to the bottom. Watch for it now. Here we go. Bah! Whoa! See how fast that is. Those stars just zoomed off of the main sequence. They're still going now. Boop, 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 go, go, bye, 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 die, 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 die. Now we're down to stars that are about 10 times the luminosity of the sun. Die, 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 die. Doesn't seem like much is happening now, so it's kind of slowing down. By the way, they're going up off the main sequence. We'll find out about that in a lecture when I get back from the East Coast. Still dying here. Still dying. A lot of stars are ending up down here, way below the main sequence. Wonder what that is. They're dead stars. You would have a pretty good idea of what the stars are doing here. Those look huge, and these are tiny stars down here. We'll get to that later. And that's the end of my movie. After, I think this is about 10 billion years, you can see that even stars like the sun are finally just about getting ready to leave the main sequence, having exhausted their fuel supply. So now this looks very, and there's still stars, these low-mass stars will be on the main sequence practically forever. So this looks very much like the HR diagram, or the graph that you would see for a globular star cluster. And the first one, when we started, looked more like a very young open cluster. All right. So the detailed and careful observations of star clusters combined with fairly sophisticated computer models were able to confirm that we really do understand how nuclear fusion causes stars to evolve and to eventually die. There's a pretty picture of what's that? Another globular star cluster. I just thought I'd put an art shot in here for you all to look at. I don't think there's any more scientific point to it. They're just very pretty things to look at. There it is now. This is kind of a summary of everything that I said in this lecture. We have HR diagrams, luminosity surface temperature plots of the main sequence. There's your main sequence. That's where it should be. That's a mass sequence or a lifetime sequence. And we've overplotted here several different kinds of star clusters. The purple data show the observations that have been made for this H and Chi Perseus cluster. This is a very young star cluster, only 14 million years old. So even stars that have a main sequence lifetime of 15 million years are on the main sequence. Very massive stars, very luminous, very powerful, still belting it out on the main sequence. Then we go to the Pleiades. We said that was about 80 million years. Upper main sequence is finished. It's gone in the Pleiades, but still, there are some very massive stars with lifetimes of 100 million years just dying right now in the Pleiades. Then we go to the Hyades. That's about the oldest open star cluster known, and these main sequence stars are finished. They're gone. They're disappeared, not found there. Here is the termination of the main sequence of the Hyades. These correspond to stars that live about 2/3 of a billion years, 650 million years. So that's apparently when the Hyades star cluster was formed. And finally, we're getting to very old star clusters here where the main sequence turnoff is getting to be fairly close to where the sun is. That cluster is 7 billion years old, and a globular star cluster would turn off about here as a turnoff right where the sun lies on the main sequence, because that's just about to croak and leave the main sequence in the oldest star clusters that we know. I want you to understand this in some detail because it's not just essential for knowing what the oldest stars are. This is essential for figuring out the evolutionary history and age and origin of our entire universe. A lot of it hangs on whether this stuff is correct. And this has been quite well tested, so I have a great deal of confidence in it. But I want you to know where it comes from and how it was worked out, what the observations were and what the theoretical interpretation was that led to it. So I will finish with a philosophical, let's see. No, I'm not going to do that yet. I'll just finish with a philosophical point here that what happens next is even much more interesting. So, yes, of course, we need stars to be on the main sequence. And yes, it's wonderful to have a very steady, reliable source of energy, heat, life for evolution to take place on a planet in that system. So we're very thankful for the sun. But if that's all that stars ever did in their life, was simply to give off heat and radiation and light very steadily, it wouldn't be enough. We would not be here because there wouldn't be any of the ingredients necessary to make life in the first place. And stars that were first formed when the universe was born didn't have any of the heavy elements necessary for life or any kind of chemistry at all. That had to come first, and pretty much the only way that that can happen, that can come about, is by these stars ending their main sequence lifetimes and dying, hopefully in the most spectacular way possible. So not only are stars have to live so that we can live, but the more interesting thing we'll find out in the next lecture is stars absolutely must die so that we can live. I'm not trying to be poetic or theological. It's an absolute fact, which we can prove.